cookie. No, you're not a cookie, you're a dolly. Oh no, here we go again. Oh no, cookie, dolly, cookie, dolly. Oh, what the hey? Eat oatmeal. Hug, hug, hug. Eat oatmeal. Ah.
Monsieur?
Oh, yes. Well,
Now, what starts with the letter C? Cookie starts with C. Let's think of other things that starts with C. Who cares about the other things? C is for cookie. That's good enough for me. C is for cookie. That's good enough for me. C is for cookie. That's good enough for me. Oh, cookie, cookie, cookie starts with C. Oh, C is for cookie. That's good enough for me. C is for cookie. That's good enough for me. C is for cookie. That's good enough for me. Oh, cookie, cookie, cookie starts with C. Hey, you know what? A round cookie with one bite out of it looks like a C. A round donut with one bite out of it also looks like a C. But it is not as good as a cookie. Oh, the moon sometimes looks like a C, but you can't eat that. So, C is for cookie. That's good enough for me. Yeah, C is for cookie. That's good enough for me. C is for cookie. That's good enough for me. Oh, cookie, cookie, cookie starts with C. Yeah! Cookie, cookie, cookie starts with C. Oh boy! Cookie, cookie, cookie starts with C.
Good morning. How you doing this morning? Doing okay? Okay. Kevin Great says thumbs up. Okay. Fantastic. Good to have you all for another virtual lecture, fully virtual lecture. So a few reminders per the scrolling ticker at the bottom of the screen. Number one, please remember to put your quiz in. So by sometime tonight by 11:59 p.m. Please submit your quiz. Again, 10 multiple choice questions, just like the last format. So just remember to get that in. Number two, your homeworks are due tomorrow. Okay, I pushed. You can check online. The official deadline for submission has been pushed back to 11:59 p.m. on Friday. My hope is you don't have to use that. But if you need help, keep in mind that there are office hours, 1 to 2 today for me. I believe 11 to noon tomorrow. If I my TAs here, maybe they can tell you the FAMU side TAs is give me a thumbs up if it's 11 to 12 tomorrow. I can't remember off the top of my head. Maybe put it in the chat if you don't mind. So those are our big things. Next week is when your proposals are due. I misspoke. Last lecture that was clarified over the announcements. So that's the course update for the moment. So I wish you luck on your assignments. Again, happy to see you in office hours if you have further questions. All right. With that, today we want to cover more of direct collocation and actually code up our own direct collocation, our own direct collocation formulation and solve it. So, and David J is giving the thumbs up on that. Fantastic. Wonderful. Let's go to the board. All right. All right. So, direct collocation continued. Fantastic. All right. So last time we basically went through the concept of direct collocation as representing both the inputs and states as decision variables. So recall Direct collocation represents inputs and states as decision variables. That's just like multiple shooting. Multiple shooting does the same thing. But it approximates the integration with splines. Okay? And what were the benefits of that? Seems one downside is that it's an approximation, a further approximation of your dynamics, okay? Because your dynamics might not move along a spline, okay? But an advantage was that it makes the constraints simpler, all right? It makes them not the result of a time marching integration. Okay. So it does not use time marching integration or shots or shooting. Okay, so this makes any constraints we have associated with the evolution of the trajectory, the dynamics, simpler algebraically. Often they will just be an algebraic expression, which means that one, they're faster to execute. We can run code much faster that checks whether or not that checks whether or not the constraint is satisfied, and that's useful for your solver. But very often, those constraints are now we can now write them analytically, which means we can take derivatives and thus have gradients and Jacobians also written in very, very fast executing code. Okay, and that's what we aim to do today. But before we get to too many details with that, I do want to cover a little bit more on direct collocation. Okay. On implicit integration methods. Okay. So we do not explicitly integrate our dynamics forward in direct collocation. We have decision variables for states, and we add constraints such that the spline between them obeys our dynamics, right? And we talked about how that spline that connects them can be all kinds of splines. It could be a linear spline. It could be a quadratic spline. It could be a cubic spline. You could go to quartic splines, although I can't say I've seen that up to a quartic spline. I've seen people use Fourier transforms. Fourier series to connect states. I've seen that. All right. If you start using things called orthogonal polynomials, it actually becomes a different category than direct collocation. It's called global collocation or pseudospectral methods. Okay. For another time, though. Okay. But you can have many splines. Okay. Has anyone ever flown on an airplane and they say, "We know you have many choices for airlines, and we're glad you chose us"? Well, you have many choices in splines. That's up to you. Okay? So choosing a spline type chooses an integration approximation method. Okay, the simplest one called forward or explicit Euler. And that's saying that if you want to know what your next state is, call it qi plus 1, well, it's approximately equal to your previous state, qi, plus the derivative at that state, qi dot, times your delta t, your change in time. Now that has a very typical name in integration. That's h. That's your time step. Okay? That's your time step h. Cool so far. Great, no comments. So that comes from the definition of a derivative in the fundamental theorem of calculus. You know, that comes from the definition of a derivative, dq dt, is equal to the limit as h goes to 0 of q of t plus h minus q over h, right? Which is approximately equal to q of t plus h minus q over h when h is small. So if you solve this out, you multiply your derivative by h, you put your q on the other side, and boom, you have this equation, right? Simplest integration scheme. Probably one of the first you'll learn. Okay? And not a and I use it all the time, by the way, in my trajectory optimizations. Okay? So it is the least accurate. So it is the explicit Euler is the least accurate of prominent schemes. Okay. Now, if you wanted to go, if let's say you're doing integration in general, okay, you're just doing you're trying to forward integrate your dynamics. We've heard of this now, explicit Euler. There is another very popular approach. It starts with R. Anyone want to tell me what that is in the chat or on the headphones here? Runga right? So you might say, well, I know where this is going, Dr. Kubicki. You're going to do a Runga method, which basically does multiple approximations of the derivatives at different points, then combines them in some kind of way. It's actually not what we're going to do today, because in trajectory optimization, we have information that Runga wouldn't have access to, because so you got explicit Euler, because in our trajectory optimization problem, we have our time, we have our state q, we have decision variables along the whole trajectory. We have knowledge of the future, or at least what we expect the future to be. Okay? So we can use information not just from our current state, from our current time, I should say, but from the state at a future time. So we don't need to only use a derivative at our current time. We can also use our derivative at a future time. We have that luxury in trajectory optimization. Okay? So, in trajectory optimization, we have access to the state values at future times. And thus can use that information to improve integration. So that gives us the opportunity to not just use qi dot, we could use qi plus 1 dot in this equation. Okay? So where q, let me label it. It's called implicit or backward Euler, where you're using the derivative from the future in order to help imply your state for the get your state in the future. So the equation for that is quite simple, where qi plus 1 is approximately equal to qi plus qi plus 1. So the derivative from the future times delta t. That's more accurate than explicit Euler. So you can see how if you were setting up a direct collocation problem with your defect constraints, your defect constraint would now be dependent upon a different derivative. And therefore, will depend upon different states along the trajectory. So you have explicit Euler, implicit Euler. You could also use both the forward and backward. You could use, and we call that trapezoidal or crank Nicholson. Spell that right? Make sure I get that spelled right. Up in your faces. No H in Nicholson. Wrong one. Camera view. Nicholson. Okay. Where you use both the forward and the backward derivative, you average them. Okay, that's like that's how you do a trapezoidal integration. So you say qi plus 1 is equal to qi plus qi dot qi plus 1 dot end quantity over 2 times delta t. That's great. That tends to be more accurate what I will point out as a practical consideration for you folks, it's great. I love using it. We use it all the time. And we use it for our model predictive controllers all the time in the lab now. We use a trapezoidal integration scheme to run our trajectory optimizations. They're great. One thing you got to be slightly aware of is it can cause ringing in the solution. What that means is is that you might have some state over time and some input over time that comes out of your trajectory optimization. And this might be your trajectory it comes up with for your problem. This thing. And depending upon your setup of your problem, trapezoidal might give you, let's just say, this kind of smooth trajectory. And in robotics, we tend to like smooth trajectories because they don't, you don't want to ramp things back and forth too hard in robots. Or it might give you this trajectory. And why is that? Well, if your derivative is dependent upon your control input u, and you are averaging your derivatives in order to come up with your next state, if the average of these 2 points is the same as this, it might give you this ringing solution because the average signal between nodes is the same whether it's ringing up and down or it's smooth. Now, in practice, we can get rid of that as long as you have, it's helpful if you have some kind of, some value of u in the cost function. Okay? Because if you have a value of u in the cost function, it will see, the optimization will see that, oh, having super high and super negative values is a bad idea. And it will smooth it out for you. Okay? Just be aware of that with trapezoidal. Okay? And finally, we have Hermite-Simpson. Okay, as an approach. And this is even a higher order, okay, where Q I plus 1 is equal to Qi, that's all the same, all approximately equal to, plus 1/6 times Qi dot plus Qi plus 1/2. What? Dot. We'll get to that. Plus Qi plus 1. And there's a coefficient of a 4 in front of Qi plus 1/2 plus 4, all times delta t. Okay? That's Hermite-Simpson, and it's probably the highest order method I tend to see in direct collocation. Okay? Now, how does this work? Okay? So, I'm going to draw out our time and our state Q. Okay? And so what that means is, we'll say this is our time I. And this is our state at some time Ti plus 1. So our previous time and our current time and our next time. All right. But in the middle here, we have a state at Ti plus 1/2. That says Ti plus 1/2. Ti plus 1/2. And in direct collocation, that's going to be a decision variable, which I circled in blue. Here's a decision variable that I circled in blue. That's what we're used to having, right? But for Hermite-Simpson, you have to add yet another decision variable. Here, I'll circle in red. We have additional decision variables at the half time step step. Okay, so you're going to add more of them, so that way you can compute the dynamics at the half time step. Okay? Now you've added an additional decision variable to the problem. Here's a good rule of thumb if you're setting up any kind of optimization problem. If you add new decision variables, you probably should be adding more constraints. Okay? Otherwise, that decision variable might just be floating around doing nothing and not mean anything. Okay? So for Hermite-Simpson, you got to add more decision variables and more constraints. So you've added this one decision variable at each half step. You also need to add the constraint that Q I plus 1/2 is equal to 1/2 Qi plus Qi plus 1. So the average of the two plus 1/8 Qi dot plus Qi plus 1 dot times delta t. So you have this additional constraint for your half step. Okay? A little tricky. Notice how we're in the business now of adding a bunch of variables to our design problem, to our optimization problem that didn't necessarily need to be there. And yet, that is the way that the field likes to solve these problems. It likes to just add more decision variables because it might give us something. It might give us the ability to solve these problems faster, to solve them more reliably, or to give us more accurate representations of the dynamics even. Okay? So adding decision variables is a tool in your optimization toolbook. In fact, you did this in homework 1. We talked about how we had to add a decision variable to create that absolute value function. Okay? Same idea here. Adding more decision variables, but you got to make sure you add constraints. All right. So just as a sort of review, an overview, if you have a linear state spline, then you either have explicit Euler or implicit Euler. Okay? If you're using trapezoidal, you are finding the average between this derivative, which is sort of like this slope, and the next slope here, Okay? And then you're going to average those slopes at some point. It's implying a quadratic spline. So quadratic spline, that's your trapezoidal. And if you have a cubic spline, you are implying a Hermite-Simpson integration scheme, which requires the extra variable. Which makes sense. If you want to have a linear spline, you only need one variable to define how that connects to the next point. Okay? You have a starting point and you have the slope. So that slope tells you how you're going to get to that next point. Okay? You know, quadratic spline, all of a sudden you have an extra degree of freedom for a quadratic. You now have its curvature, its acceleration, right? So you need an extra data point to define it. So that's why you use two approximations of the derivative. Okay, the forward and the back, the first one and the second one. For the cubic spline, you have a third parameter to your spline, so you need another piece of information to define it. That's why we add another point. Okay, that makes sense. All right. So we're going to pause there. I'm going to go straight to coding. So if anyone has any questions, now is a great time while I take a swig of my coffee. 3, 2, Great. By the way, I believe I fixed that recording issue, so this should all record nicely and be uploaded right after this lecture. So with that, let's talk coding. I don't know, kind of the fun part. You actually get to see it in action. So we're going to use a couple of tools today that you may or may not have used before. Okay? So we're going to code direct collocation. We're going to code our example from last lecture where we're going to be moving a block from one point to the other. It's a simple one, but gets the point across, right? Okay, we're going to code direct collocation. So we're going to do a few things we're going to learn. A big one is the symbolic toolbox in MATLAB. Those who haven't used symbolic toolboxes before, they are wonderful for just trying out new research ideas. Like you can whip up simulations of mechanical systems, the equations for them so quickly. It's really cool. I recommend wrapping your head around symbolic toolbox as best as you can, as early as you can in your academic career. Okay, and also from an optimization standpoint, we're going to supply derivatives to optimization solvers. Okay? All right. So those are going to be the two things we're going to start with, okay? In terms of the problem we're actually going to solve, we're going to do the minimum time double integrator. Just like we talked about in the last lecture. It's our example. Okay, we are going to have our block. It's going to be sliding. We're going to do it without friction. Some input f of t. we have some distance we're covering, s of t. It's going to start at s equals 0 and s dot equals 0. It's going to end at some s final, which we'll say is 5 units away, and s dot final is equal to 0. And we're going to limit our force to be between minus F max and F max. And we'll say that F max equals 10 and M equals 1. And we don't want to forget the most important constraint of all, that we don't want to give our robots the ability to time travel. Right, Kevin Best? So our final time must be greater than or equal to 0. Okay? No time travel allowed, Kevin. Sorry. Okay? Right. Fantastic. All right, so that's what we're going to want to code up. Let's cover some basics, and we're going to open up MATLAB. We're going to go through some of them. All right, what could possibly go wrong with my Twitch streaming setup? Absolutely nothing. All right. Okay. So here we are, back at our MATLAB code. This is our multiple shooting optimization. You'll remember that. We're going to make a new folder for direct collocation. And we'll start with a clean slate right here. Okay. No more code. So I'm going to take you through some critical things, particularly the MATLAB symbolic toolbox. Now, many of you're doing a great job of making sure you have the right toolboxes installed in MATLAB. Now, I know some of you are doing Julia, and some even Python, you're doing this. So, that's wonderful. Go on with your bad self, I believe, as the children say. That's awesome. In MATLAB, if you want to make sure you have all the toolboxes installed correctly, you want to type in VER or ver for version, and it'll tell you VER, enter. It'll tell you, oh, what do I have installed? And I have all my favorites. Okay. I've got my control systems toolbox, got all my robot toolboxes. You want to make sure you have the optimization toolbox. But importantly today, we want to make sure you have the symbolic toolbox installed. And most languages have some symbolic ability to do this kind of, to do symbolic operations. It's really neat. If you need to add more things to MATLAB, you go up here to apps. It's up at the top. Okay, you can get more apps or install packages and search for it. Okay. So for those who've never seen a symbolic toolbox before, they're awesome. Okay. And we're used to saying, hey, if A equals 1 and B equals 1, then hey, what's A plus B? It's 2. We're used to that in MATLAB. These are dealing with floating point numbers inside of the code. It's how it works. It's all fun. In addition to that, we also have the symbolic toolbox, where I can say sim and then A. And what it's going to do is it's going to create a symbolic variable called A. Let's say if I want to create another symbolic variable called B. If I were to say A plus B, oh no, I've already assigned them as 2. Okay, let's clear everything. So clear everything. So you want to say A, you can create symbolic variables A and B. So what you want to do is create SYM and then list all your variables you want to be symbols. Okay, and then hit enter. And these should both be, did I not clear everything right? Okay, sims A, sims B, A plus B. There we go. So SYMS, apologies. So sims. And it creates a symbolic variable a and b. Then when you hit a plus b, what comes out? You have a plus b, a symbolic expression. So you can do symbolic math, right? So you could say, I want c equal to a plus b. And I want to know what c squared is. It's going to do a nice algebraic expression of c squared. Oh, a plus b squared. How about that? Well, let's say I want to FOIL this out. I want to expand it. I could say, oh, expand expand c squared. And look, it FOILs it out. How nice, right? You can do all kinds of cool algebraic operations in symbolic toolboxes. All right, Mathematica, I think, is probably the gold standard of symbolic software packages. But MATLAB, I believe, bought Maple years ago. So if you work with Maple, I mean, you have basically Maple's ability to do symbolic operations here in MATLAB. So, which is great. So you can do all kinds of cool stuff. What I do all the time is I set up my equations of motion for mechanical systems and rederive them using the symbolic toolbox. All right. So in addition to algebra, you can do calculus. I could say, hey, what's the derivative of c with respect to a? Tell me. Oh, it's 1. Okay, apparently. I don't, yep. The derivative of a plus b with respect to a is 1. It got the answer right. How about that? I can say, hey, what's the derivative of c squared with respect to a? I believe it should be 2a plus 1. 2a plus 2b, close. So you can take derivatives symbolically. You can see, I hope you all can see how that will be especially useful for optimization where we need to create, where we're often asked to compute derivatives. Okay? So, in addition to that, you can just take not just normal derivatives, where you would say, I want the derivative of blank with respect to blank. You could also take the derivatives of vectors. So we can create vectors of vectors of variables. Okay, so we have a and b. We could also create a vector called a, b. Right? And hey, there's a vector with a and b in it. And remember, we have our variable c, which is equal to a plus b. What if I wanted to take the derivative of c with respect to a and b? Well, that's a vector. We could take the derivative of the scalar with respect to a vector, which in our class we learned, or in other classes, has a special name, starts with a G. It's the gradient. Okay? And if you have the derivative with respect to of a vector with respect to another vector, we call that the Jacobian. Well, there actually happens to be a really nice command in MATLAB called Jacobian. And you could give it a combination of scalars and vectors, and it will compute the Jacobian. So let's take the derivative of c with respect to our vector a, b. And voila, it gives us our Jacobian, which is a 1/2 Jacobian. There's the answer. We could take the Jacobian of c squared. We could take the Jacobian of a vector that contains c and c squared. There's your Jacobian matrix. Nifty. Okay. So that's cool. And so what gets sent out of Jacobian and all of these expressions is all of these expressions that are printed to the screen, but we can save them as variables themselves. So I could say that J is equal to Jacobian c squared, then a and b, and stored into J. Now, let's say I want to substitute in a value for A and B to get what what a numeric matrix would be. Okay, well, we can do that. We can do that. So you want to, for substitution, you want to use the command subs, S-U-B-S, for substitute. Okay, how does that work? I'll pull up the help file so you can see help subs. And what you put in, you see there's lots of different ways to use it. The simplest one is you give your expression, which is symbolic expression. You give your old variables and your new variables. So you could substitute in not just a number, you could substitute in some other expression, right? So we'll use subs on J, and I want to substitute instead of A and B, I want to substitute in 0 and 0. All right. A little note on syntax. Note that I used a curly brace for delineating between A and B. Anyone know what the curly brace indicates in MATLAB? A square bracket indicates a vector or a matrix. In MATLAB, a curly brace indicates something called a cell, C-E-L-L. Okay? It's just another data structure that MATLAB uses to contain multiple things that may or may not be the same data type. So you could substitute in potentially not just a symbolic variable with a number and a number. Okay? You could also substitute in, for instance, subs J, A, and B, and I'll substitute in the number 0, but also the expression C. And it can do that. And 0 and C might be different data types. So anytime you're working with different data types you want to put together, you have to use a cell, which is used using the curly braces. You don't need to know a ton about that to use this command, but that's just how you use it. All right. So let's go back to inserting zeros into our Jacobian. So I'm going to create our J substitute. Our substituted Jacobian is equal to substituted J, A, and B. And I'm going to give it 0 and 0. You have J sub. You'll notice that J sub is not actually printing out floating point numbers. If you're used to saying, hey MATLAB, what's this matrix? Look how it displays it differently. That's because these are different data types. And the way you can check is you can use the command class. Say, hey, what was the class of this answer here? Of 1100. What was the class of it? And it'll tell you double. And for those who aren't computer science folks, double is just a floating point number, with a decimal point and a bunch of numbers after it that happens to be double precision, and it has more memory associated with it than a float, okay? But if you were to look at the class of J sub, say, hey, what's the class of J sub, please? Tell me. It's a sim. It's symbolic expression. Okay? So these are not the same type. So if you want to do floating point math on J sub, you can recast it as a floating point number. Let's say, so if we said double J sub, it will turn J sub into a double. At least it'll return a J sub that is a double. There we go. So the class of that answer is now a double. Okay, so that's the symbolic toolbox in a quick nutshell, okay? However, one of the coolest things we're going to try to do is we're going to not just come up with symbolic expressions like, let's look at J, okay? Wouldn't it be great if we could make a function? for which you insert A and B, and then out pops your Jacobian. So you don't have to do that whole symbolic expression. Well, if there's a way to make a MATLAB function to do that? Well, there is a MATLAB function that makes MATLAB functions. It's called MATLAB function. I am not lying. That's what it's called. So say help, MATLAB function. So MATLAB function is lowercase MATLAB, capital F function. So help, MATLAB function, generates a MATLAB function from a symbolic expression. Okay? And there are lots of different ways to use it. So let's try the simplest way, where it would say some function g is equal to MATLAB function f. So I'm going to say some function, I'll call it fun, equal to MATLAB function. And we'll put in j. All right. It created a function which takes in a and b and returns all this. So if I were to say function of 0 for a and 0 for b, it returns 1, 1, 0, 0. Cool. It's made a function, right? Now that there is just an inline function. It just created it and stored it as fun, and then we could call it as fun 0, 0. But we can also have it make a file, a function file for us. And this is the first time when I was a wee baby grad student and I started playing around with this. This was too cool. All right. So you can actually give it a file name. So I'm going to create MATLAB. So I'm going to say MATLAB function J file and create a file called jfun for our Jacobian function. All right, I'm going to hit enter. And look, over in my current functions, it auto-generated this function file. Okay, I'm going to open it. MATLAB auto-generated this. Okay, so now I can say, hey, I want to say take in J function. I want to put in 0 and 0. And it should give me 1, 1, 0, 0. How about that? Okay. So that's a taste of the MATLAB symbolic toolbox that you will need for your next homework. Okay. So that is the symbolic toolbox. Now let's get to the direct collocation part of this. All right. For that, let's go back to our board. I'll leave this up for just a quick second while I'll switch views. Okay. So going back to our direct collocation problem, a good rule of thumb, if you don't know where to start for an optimization problem, ask yourself, what are your decision variables? Okay? And we're going to, so for our decision variables, we want to know our type of trajectory optimization formulation, which is direct collocation. Okay. We'll decide on the number of points on our spline. We'll call them nodes. We'll have 10 nodes, but we'll just define that as n in the code, so that way we can just change it later. Okay. Our decision variable vector x is going to need to contain all of our control inputs, 1 through un. And our states, well, we need to know how many states we need, which means we need to know what our dynamics are. Our dynamics are very simple. It's going to be that S double dot of t is equal to f of t over m. This is going to be a two-state system. So our state vector q is going to have s and s dot in it. Q dot is going to be s dot, s double dot, going to equal s dot, and f of t over m. So this is our function of Q. Oh, this is our dynamics function. And U. Okay. So we know what our states are. Okay. So we can start filling this in. The other thing we want to know is what our integration scheme is going to be. Because if we choose Hermite-Simpson, how does that change our problem? Well, the problem with Hermite-Simpson is that it adds more decision variables, right? So we want to make sure we would know that before we make our decision vector. So let's start with just explicit Euler, the simplest one. Okay. So our explicit Euler. So we don't need additional decision variables beyond one per node. Okay. So we'll have our first state Q1. So we'll have Q1, or we'll call it S1 through Sn. We'll have S dot 1 through S dot n. Oh, I'm killing myself on space here. And finally, capital T. U1 through UN, S1 through Sn, S1 dot through Sn dot, and T, capital T, our final time. Okay, that's the decision vector. That's our decision vector. What's our cost function? Well, that's really easy. So that cost function f of x. We're trying to minimize time, right? Subject to the constraint that we don't back to the future ourselves. T, easy. We've had really easy cost functions. Okay, now we have our constraints. Okay, so let's start with our so we're going to have inequality constraints. And those are easy. That's going to be F. So it's going to be all of our U's. Can be less than or equal to F max. And minus U is less than or equal to F max. And minus T is less than or equal to 0, which is the same as saying T is greater than or equal to 0. Okay? Sometimes people will make it instead of 0, they'll make it some non-zero value. That's a bit of a detail. We're going to see if we can get away with just saying purely, it's got to be at least non-negative number. I literally did have an optimization that time traveled once. At least, okay, not really time traveled, but it chose a negative time one time. I was coming up with a legged robot optimization, and it was like a running robot. I was doing this optimization. I wanted it to get all the way to the other side of basically the room in a minimum time. And I forgot to put a constraint on time when I was computing the dynamics for when it's in the air. So the solution that it came up with was really clever. What it did was while it was on the ground, it launched itself backwards. I believe is what it did. So it had a parabolic trajectory going that way. And then once it was going in that direction, it reversed time per the parabolic trajectory, which basically launched it in that direction in reverse time. And so I got to the solution in negative time. Optimizations are really clever. Okay, pretty cool. All right, you have your constraints. You have your inequality constraints. That's easy. Then you have your equality constraints. Okay, those are, we're going to say that S1 equals 0, f1 dot equals 0, Sn equals 5, Sn dot equals 0. And of course, we have our defect constraints. And that's the big challenge here. All right. Okay. So, with this in mind, let's get started coding up our problem. Well, let's get a little bit more on the board. Okay. All right. So your defect constraints. Okay. As we talked about last class, Si plus 1 is going to equal to Si plus Si dot times delta t. Now, delta t is equal to t over n minus 1, n minus 1 because of the fence post problem that we've talked about a few times now. Okay? All right. And then Si plus 1 dot is equal to Si plus 1 plus the derivative of Si plus 1 evaluated at point I. That's going to be Fi over m times delta t. Okay. Those are your defects. For all I through I minus 1. I minus 1, again, because of the fence post problem, one fewer connection than you have actual points. And just mathematically, you check it out, you're doing an I plus 1 in your calculations. You don't want to go past your total, through n minus 1. Sorry. You don't want to go past n. I through n minus 1. So let's set up our code with our objective, our cost function, and our constraints. Okay. All right. You all doing okay today? Doing all right? Fun time? I got my coffee. Hopefully you all have your beverage of choice. Yes, good to hear, Mr. J. Doing great, doing great. So I'm going to exit out of my JFun, and as fun as it is, I'm going to delete it. No more fun today, I guess. All right. So I'm going to clear everything. I'm going to create a new script. I'm going to call it double int dir col, direct collocation. Okay. Double int dir col. That's not long enough. Double integrator dir col dot m. All right, got to clear every. Oh, you know what I forgot? My name. I made this. Don't forget to put your name on your papers. Apparently, I never learned that lesson. So, and today's date 2023-02-09. Okay, so going to clear everything. CLC clear, close all. Okay. Now we actually do very little in this until we're about to start actually making our constraints and cost function. Okay, so let's create a cost function inline. So what's our cost function? So I'm going to create a function called cost function, which takes in our decision vector x and returns the value of our cost function, which is going to be the last value of our decision vector. And you can see that from my obviously not going to be pixelated at all on your screen's whiteboard here. At the bottom, you see the t of our decision vector x. So our last value is going to be our x. Okay, so got our cost function. That's easy. If only the constraints were as easy. So for our constraints, I'm going to create an actual function. Okay, a function file, I should say. So I'm going to create a new function file. I'm going to click new in the upper right, or I'm going to hit Control N like a cool code warrior. Create a new thing. I'm going to create our non-lcon function. Okay. I'm going to save it as non-lcon, our nonlinear constraints. Okay. What do we return? We return C, and we return CEQ. Okay. All right. Okay. So we're going to create non-lcon, and it takes in our decision vector x. Okay. That's what we like to do. Now, the thing that I will point out is that this cost function is going to be something that's going to start to get pretty long. Sorry, these constraints are going to become a pretty long vector. Okay? So we're going to want to auto-generate our ability to make these constraints. Okay? Or at least do this in an interesting, more automatic way. So let's do that today. So we have, in terms of our constraints, C and CEQ. Oh, that's a function. C and CEQ. Takes in X, gives me C and CEQ. Now our C's, those are our inequality constraints. Okay. So we're going to start with C being empty. Then we're going to add to C. I'm going to say C is equal to C, but we're going to add, with each constraint, add a new element to our constraint vector. So let's start with having all of our forces being less than F max. Okay. So in order to have that, we need our constraints such that our forces are less than F max, and we got to put that into our standard constraint form. So let's go back to the board real quick and show you how we'll put that together. Because we want these as G1 of X is less than or equal to 0, that means that U minus F max is less than or equal to 0. I just took this, put it on the other side. Then minus U minus F max is less than or equal to 0. I just put that on the other side. Then I want, that's fine. Our Bestian constraint, T, is all good. So our three inequality constraints, we can just take all of our U's and subtract F max and add it in to our constraints. We take all of our U's, negative minus F max, it's in the right form, minus T, already in the right form. Now, we could always put this as bounds or linear constraints in our optimization problem, because not MathMinCon takes linear constraints. I recommend doing that in general. For today, I'm showing you just how to add constraints inside your nonlinear constraint category, okay? For non-lcon. So let's put that together. And for the defect constraint, that's for G2 of X is equal to 0. So that's going to be our 4 task constraints. Our task constraints, then it's going to have our defect constraints. So this is going to be S1 minus 0 is equal to 0. S1 dot blah, blah, blah minus 0 is equal to 0. Sn minus 5 is going to be S1. It's going to be S1 dot. This will be Sn minus 5. This will be Sn dot. Make it equal to 0. Okay? And for our defect constraint, we have to rewrite this so it's Si plus 1 minus Si dot delta t and equals 0. And Si plus 1 dot is equal to minus Si dot minus quantity Fi over M delta t equals 0. Now we have our equality constraints in the right form. Okay? So, for all of our inequality constraints, we're going to need all of our u's. Well, what are all of our u's? Let's make our lives easy by saying we grab all of our inputs and states. So we're going to say that our u's is going to be x1 colon n. Now we don't know what n is, so let's compute n. N is going to be equal to the number of elements in x, which if we have 10 nodes, that's going to be 10 inputs plus 20 states plus 1 t. That's going to be 31. So we'd subtract the 1, then divide by 3 to give us n. So we can grab our u's as being x1 through n. We can say our s's are x n plus 1 through 2n. The syntax should be very similar in Julia, for those Julia-fying this. And ds is equal to x 2 times n plus 1 colon 3 times n. And t is equal to x end. So hey, we have a vector here which has us and ds, which might make our life easy. So we want to add all of our inequality constraints. Let's define f max. The constants. Let's say that f max is 10. Let's define m is equal to 1. And let's define our final state, our final position as 5 for our constants. So let's add in our inequality constraints. This time I mean it. So it's going to be u minus f max. That's up on the board. Then we're going to say c is equal to c. Take all the previous constraints. You know what? I'm going to do this even easier. To add them in here. It's going to be minus u minus f max. And finally, minus t. Okay. All right. Those are our inequality constraints. In fact, I'm going to get rid of all of that. Make that a little nicer. There you go. That's C. Now let's look at CEQ for our equality constraints. So we're going to have, as our equality constraints, our first one are our task constraints that are S1 needs to be equal to 0. DS1 has to also equal 0. Starts at rest, starts at 0. Then we want it to end at S final, so S end minus S final. and we want dsn to equal 0. Those are our equality constraints thus far. Now we can add more equality constraints, CEQ, by saying CEQ colon, adding to those constraints. So what are our defect constraints? So if you go back to our board, it's going to be SI plus 1. So that's going to be S2 colon end. So the second one through the end minus S1 colon n minus 1. So Si plus 1 to the end minus S1 to the n minus 1 minus ds1 colon n minus 1. So that's the first through the n minus 1 of all of my ds's times delta t, which was t divided by quantity n minus 1. There. Now, I need to add my defect constraints for my second state. So CEQ, S. All right, now we have our other equation. I'll put it, now from the board, it is ds, 2 colon end, minus ds 1 colon end minus 1 minus quantity u 1 colon end minus 1 divided by m times t divided by quantity n minus 1. I know we're about out of time. Next will be the last defect constraint. The only thing I want to check here, I'm going to do a quick debug check before we try to run all this. I'm going to run non-LCON with zeros. I want to say 4 of them. Just a quick debug check. It's a good check if you want to just try out your function before you use it. You can use the keyboard command to stop the execution of your command. And I could say, hey, what's u? Okay, let's say this 31. Good, they are the right size. So size of u and 1. Perfect. Great. Getting rid of the keyboard command, quit debugging. So here is our non-LCON command. All right, let's see how quickly we can turn this into fmincon. All right, so back to our double integration scheme. We're going to say fmincon. We're going to give it our objective function, which is our cost function. We need to give it an x0, okay? I'm going to give it a bunch of 1s as my initial, x0 is our initial guess. I'm going to give it 31 of them, okay? Then you no A matrix, no B matrix, no AEQ matrix, no BEQ matrix, no LB, no UB, but we do have non-LCON. So at non-LCON. And all right, friends, ready to run this? See what happens. Local minimum found that satisfies the constraints. Oh my goodness. Did it do it? It did it, friends. It found the minimum time as 1.4 seconds. And look at our control inputs. I'm going to plot our control inputs, everybody. Watch this. Watch this. I'm going to do it. It's going to be so much fun. Thank you for taking an extra 2 minutes. But the answer, 1 colon 10, that's going to be our first 10 points in our decision vector. What does it look like? I said, what does it look like? You can see that. It says, look, maximum force. Then halfway through, stomp on the brakes. Congratulations, everyone. We did it. Only 3 minutes over. I knocked my thing over. Anyway, I'll stop recording here. this is the official end of lecture. Thank you all for coming. I have you take a few questions before as I pack up. Take care.